Hello, my name is Vasilis, and today I will present you a speech emotion recognition approach which preserves users' data privacy by combining federated and semi-supervised learning. This work has been performed as part of my PhD in the Eindhoven University and has been funded by the European Distributed Artificial Intelligence System project. I will start this presentation with a small background and definition related to SHARE, and then I will briefly explain the concept of federated learning, which is the core of our work. Next, I will discuss the centralized regimes together with their limitations, and with that, we will see the need for federated approaches while performing speech emotion recognition. Lastly, I will present the experiments that have been performed in our work together with the conclusions that we have drawn from them. So starting with the speech emotion recognition task, the objective of this task is to detect users' emotions from their speech data. And we are particularly interested in to detect 6 core emotions from which all other emotional states can be combined. In the past, this task was performed by using some arbitrary handcrafted features from the data to detect the emotions, but later on we exploited the classification algorithms such as support vector machines to predict emotions. And with the rise of deep learning, the focus has now shifted on training deep learning models to recognize patterns from the raw audio and determine the emotional state of the users. And now most of the deep learning approaches nowadays utilize the centralized approach where the data are collected to a central location to train a model. However, in our work, we focus on a distributed machine learning environment, and in particular, we propose a federated speech emotion recognition approach. So before moving on to the presentation, I would like to make a small introduction to federated learning, since this is a core component for our work. A simplified federated learning scheme is shown in the picture on the right, where the model is trained, where the model training is being performed in federated rounds. Each federated round consists of three major steps and starts with the server sending all the data, all the participating devices, the current model weights. After that, each device trains a local copy of the model in their own data, and by taking basically a few stochastic gradient descent steps, and once this training process is being performed, the new model weights from each local model are communicated back to the server, which is responsible for aggregating all the updates to create from those a new global model. Now, there is a lot of ways in which the aggregation can be performed, but the most simplistic and effective one is federated averaging algorithm, which we have utilized during our work. So in this way, we see that the models are being trained with no need for users' data to leave the device, and in this way, we can achieve data privacy by design. And in addition to this, we also have the benefit of processing the data closer to the source and thus relaxing the computational stress that we put on the server side. So now that we have understood the concept of federated learning, we can now move on and see the currently developed centralized regimes for speech emotion recognition and and then examine under what assumptions these techniques have been working. And from this, we can see if there is a feasible, realistic application using these approaches. We can imagine that the centralized training process as a four-step process shown in the bottom, where we collect the data from the user side and aggregate them in a central repository. After we have acquired those data, we can train our machine learning model and then deploy it in order to detect the emotion of the users. So from this pipeline, for this pipeline to work, however, we assume that the user's data can be easily accessible and can be sent to the server side. In reality, however, the rate at which such data are produced is much higher than the one that central repository can actually process. and the cost of communicating such data over time is constantly increasing. But a more important restriction is that such data aggregation is infeasible because of the data regulation that often come with this kind of data, and which can highly limit the actual data that the server will actually receive. And if we couple this with the increased concern of the users about their privacy and their willingness to share their own data, we most probably end up with too few samples to train our model. So in the end, our model are trained with the majority of collected data originated from control environments and with too few natural speech data. And this poses significant challenges to deep learning approaches to produce models that have a high detection rate and can generalize well when they're exposed to new users or different environments. So the restriction due to the privacy regulation and consents poses major challenges in the training of such models, and thus we try to eliminate these problems by shifting to a federated speech emotion recognition approach. So when moving to federated settings, we can see that most of the process is now shifted to the user side, with the server only communicating individually with its device to send the model updates. In this way, we can achieve data preservation and expose our model to basically unlimited amount of natural data, since the user can constantly generate new samples and even more users are exposed to the process. However, while this approach creates a lot of opportunities, first need to solve some challenges. Firstly, the fact that we perform the model training in users' devices, and these devices have restricted computational capabilities when compared to servers, render most of the developed models and model architectures, such as recurrent neural networks and transformers, unsuitable for federated learning. This means that we need to first find a model architecture which is small but can capture the complex emotional patterns present in natural speech. But an even more major challenge is that the labeling process is now completely entrusted to the users. So this essentially means that the quality of labeled data we acquire is determined by the effort of the users. So assuming that the on-device labeled data is sufficiently available, or the data can be easily labeled through user interaction or through some kind of label function, is clearly something unrealistic in share. And this results in most of the data available on device to remain unlabeled. So to tackle these two challenges, in our work we propose a CNN-based architecture with an attention layer that expands through all three dimensions of convolutions, and we try to capture in this way the emotional cues that are sparsely scattered across the natural speech utterances. In addition to that, we combine the federated learning with on-device self-training in order to jointly learn from both labeled and unlabeled data that are present on the user devices. More specifically, the overall model pipeline is shown in the left of this figure. We see that our classification model takes as input log-mel spectrograms of 2-second log audio samples. Briefly, I will say that we calculate those spectrograms by performing short-time Fourier transform on small window of our audio sample, and then we plot it over the log-mel axis. So after we have calculated the log-mel spectrograms of the audio sample, we pass them through 4 consecutive blocks, which have the structure shown in the middle top box. Essentially, in each block, we take the input and we perform 2 convolutions in parallel, one on the temporal and another one on the frequency axis. So by doing that, we can obtain fine-grained features, and then we can coordinate these 2 convolutions afterwards to perform yet another convolution in order to find any high-level feature that is present in both dimensions. So after these 4 convolutions, we pass our model through an attention layer, which creates a 3D attention map and tries to capture information that exists on temporal dimensions such as rhythm and beats, and spectral features such as harmonics and any possible interaction across the channel dimension. Then we reweight our initial input by multiplying this attention map with the input before feeding it to the softmax classifier, which will then produce probabilities for each emotion to be present in the input audio file. To exploit on-device unlabeled data, we utilize self-training based on pseudo-labeling. So this process starts with training a model using the available label data. After we have acquired this model, we use it to annotate the remaining unlabeled data. And in the final step, we train our model using both the labeled and the unlabeled data, pseudo-labeled data, sorry. However, for this process to be effective, the annotation of unlabeled data must be done correctly, and especially in federated settings where the device might have different data distribution, the risk of generating faulty pseudo-labels from our unlabeled data is highly increased. So to tackle this problem of overconfident predictions and select only highly confident pseudo-labels, we perform temperature scaling on the logits before we pass them through the classifier. And we also combine it with a dynamic confidence threshold that starts from a small value and gradually increases as the rounds progress, following a Gaussian scheduler that is also taking into account its device participation in the training process. Specifically, in the local train step, the received model is trained on equally sized batches of labeled and unlabeled data using categorical cross-entropy. So since the labeled data are far fewer than the unlabeled ones, the labeled batches are created by randomly selecting data from the available on-device labeled data. And now for each pair of batches that we have, we train the model in the labeled batch and then create prediction for the unlabeled one. Then we further train our model with the pseudo labels from which our model confidence is above current threshold T, and then perform back propagation to update the model parameters. We perform this process for all the unlabeled batches, and the final local model's weights are sent back to the server. So in this way, we given enough training rounds, we ensure that all the unlabeled instances will be exposed to all the available on-device label data, improving in this way the efficiency of local models predictions. I will now move on to present you with the evaluation of our work. As an evaluation metric, we utilize the unweighted classification accuracy and chose the improvised part of the EmoCap dataset for our experiments. This dataset contains 5 dyadic dialogues and has a total of 10 speakers. Before moving into the experiments themselves, I want to briefly mention the data splitting procedure, since it is a key point to produce a realistic distribution of data among the devices. We can partition our data based on the speakers present on each device. So we can either have one or multiple speakers per device, simulating scenarios that where one device belongs to one particular user or to multiple users accordingly. But we can also split it based on the overlap between the speakers on the train and test sets, which in the case of non-overlapping speakers between the two sets, this scenario is known as speaker-independent share, and in that scenario we actually test the generalizability of speech emotion recognition approach to when we expose it to new users. So based on the aforementioned splitting, we can see the 4 experiments in this table. For the speaker-independent experiments, we utilize a leave one session out strategy, where we perform different runs with all 5 possible combinations of the 4 sessions as train sets. And then we test our model in the remaining session. And from all those runs, we calculate the mean average accuracy, and we present this result during the result section. For the speaker overlap case, we created 5 distinct cross-validation train test sets, and again measured the mean average accuracy over all 5 runs. Lastly, when the non-IAD notations are in place, we refer to the speaker distribution across the different devices and simulate the scenario of one speaker per device in particular. We created a baseline by performing supervised experiments in both centralized and federated settings, and in this way we established an upper bound of performance that we can expect from our model and compare our results with other attention-based architectures. From the results, we observed that our model, despite the simplicity, is within 2.5% from the recent state-of-the-art approaches, while relying on additional, which actually relying on additional techniques such as transfer learning to improve their performance. Additionally, we note that in speaker overlap experiments, the accuracy in both centralized and supervised federated settings uh, is increased substantially, and this verifies that the generalization is still an open research question for speech emotion recognition. Now, while we move from the centralized to a federated setting, we notice that our model can retain a high level of accuracy, with an accuracy gap between the centralized and the federated models of approximately 4 and 2% for the speaker independent and speaker overlap experiments. So this indicates that utilizing federated learning to develop highly accurate privacy-preserving speech emotion recognition systems is indeed feasible. And we also evaluated the performance of our model when on-device label data are scarce. So for this realistic scenario, we employed federated self-training to determine the obtained improvement versus a fully supervised federated approach, where we only utilize 10% of the available data as label samples. So to illustrate the performance gain of our federated self-training approach over the supervised federated learning regimes, we performed supervised experiments with identical labeled subset. So when we compare the two approaches for 10% of data available, we notice that our method utilizes on-device unlabeled data to improve the model's performance significantly across all four the experiments, with an average increase in accuracy by 8.67%. Um, Additionally, from the non-IID experiments, we noticed that both supervised and semi-supervised models retain their accuracy, with the latter to even improve the recognition rate. These results actually suggest that our model does indeed learn speaker-independent features, but the more important remark from this is that SER is feasible in federated settings, even under highly non-IID speaker distributions. And this comes in contrast to other tasks such as speaker detection, where this kind of distributions pose a significant challenge during the training process. So to conclude this presentation, we presented a federated share approach to retain users' privacy that can now train on large amounts of natural speech data, which previously was not feasible in centralized approaches due to privacy regulations. To avoid common pitfalls about unrealistic assumptions on federated settings, we expect most of the on-device data to remain unlabeled and utilize them via self-training. In addition, we propose an efficient CNN-based architecture which utilizes an attention mechanism to capture sparse emotional cues in intelligence while having a model size suitable for edge devices accelerators. From our findings, we noticed that share is feasible in federated settings when we can obtain a model with accuracy close to centralized approaches. Additionally, we identify that non-IID speaker distributions do not pose a challenge in federated set tasks, in contrast to other type of acoustic recognition tasks. As a final remark, we note that while on-device self-training is very effective is still relying on a few high quality labeled samples. However, noisy labels can still exist in federated settings and could possibly hurt the final model's performance. So, identifying such noisy labels is one of the future of work of our research. So with that, I'm closing my presentation. Thank you very much, and I'm open to answer any questions that you might have.